Hello everyone, this is the BADM A724 Quantitative Methods and Business Analytics. This is lecture 4. This is your instructor, Dr. Frank Dian Shea. In this lecture, we're going to cover numerical description of data, central tendency, moving average, dispersion, standardized data, percentile, quartiles, and box plots, and correlation. Numerical description. We talked about the visual description of data last time. Now let's talk about the numerical description. There are three key characteristics of numerical data. They are central tendency, dispersion, and shape. Central tendency. Where are the data values concentrated? What seems to be a typical or middle data values? Okay. For dispersion, how much variation is there in the data? How spread out are the data values? Are there unusual values, extremely unusually large or unusually small? Right? And the shape of data. Are the data values distributed symmetrically, or skewed, or sharply peaked, flat, or bimodal, or trimodal, or multimodal? Right? So central tendency, dispersion, and shape are the three key characteristics of numerical data. Okay. But first, about central tendency. The first and most common way of measure a central tendency, familiar one, we're all familiar probably already, is the mean or the average. Right? For the population, we use mu, Greek letter mu, to denote the population mean. And that defined as a big sigma, that's a sum of xi, each individual value in the data set, in the range, right? Added up from the first one, I equals 1, to the last one, n, capital N, divided by n, the capital N, the total number of observations in the population. Right. Basically, just add everybody, add everyone, and divide by total number. That's mu for the population. For samples, right, we draw a sample from the population. So we do not use mu, we use x bar as mean for samples. And it's defined almost the same. Xi, each individual values in the data set or in the range, and from the first one until the last one. Remember, please notice we use a lowercase n instead of capital N for sample. Right? So total number of observations in sample is small n or lowercase n right here. And also the sum of this is divided by n undercase lowercase n to get the sample mean. Okay? Straightforward. Right? That's mean is a familiar measure of central tendency. Right? Like the mean, for example, for your course grade, your test grade, we can calculate the mean, or the mean salaries of everyone in the company, or mean income of everyone in the United States. We can calculate that. Okay? In Excel, we can use a function equal average, and in each cell, in a cell in Excel spreadsheet, it types equal average. As you start to type average AVER, you see the pop-up menu showing different functions, and then give them the data range of data, and then is an array of data values, and then you hit return. The Excel function will give you the calculate mean of the data. Okay. Another measure of central tendency is the median. Right? Median, or M, is the 50th percentile or midpoint of the sorted sample data. Two key points here: midpoint and sorted. So you have the sorted data from low to high, from the smallest to the largest, and then you find the one in the middle, right? And you may ask, is there like a middle one in any group of data, any array of data? We'll get to that point in a second. Median actually separates the upper and lower half of the sorted observations. Remember, we chose the 50th percentile or the midpoint. So, and there are half of the data points below that point, below the middle point, and half of them over that midpoint, right? So if n is odd, number of observations is an odd number, like 3 or 5 or 7 or 9, right? Let's say n is 9. Which one is the median? Right? Let's say it's 5. Which one is median? The third one is the median, right? If the n is 7, which one is the median? Right? The fifth one. No, wait a minute. Sorry. If the n is 7, you get 1, 2, 3, 4, 5, 6, 7. You know which one is the median? Number 4 is the median, right? The fourth one is the median. So if n is odd, the median is the middle observation in the data array. That's easy to find. But what if n is even? In other words, you say you have 4 data points in your data set, 4 numbers. How do you find the median? There's no one in the middle, right? Then you take the middle 2. So if n is even, the median is the average of the middle 2 observations in the array. Then you can find the median, okay? Finding the median, basically you arrange the data in ascending order from low to high, and then count the number of values in the data, right? You count it. If it's even, the median is the sum of the middle 2, right? If you count is odd, you find the middle value in the data. So that's how you find the median. Okay? For example, here are the 10 test scores, right? Random order, right? 68, 98, 76, 83, 94, etc. Right? Find the median. How do you find the median? And first, you sort the data. There are even numbers of observations in the data set. And then you sort it from low. The low is 65, the high is 98, right? And there are 4 on this side, 4 on this side, and 2 in the middle. So since the n is even, or the even number of observations in the set, you find the middle 2, which is 83 and 85. Right? And you find the median, you average the 5th and 6th observations, the middle 2, 83 plus 85 divided by 2, you get 84. That's the median. Okay? That's the central tendency. Another way to measure central tendency is mode. Now, what is mode? Right. Mode is the most frequently occurring data value. Whichever value that occurs most frequently in the data set, that's your mode. Right? You may have multiple modes or no mode. Okay? Let's look at this P ratio data we just looked at. Right? There are a random sample of 68 standard poor 500 stocks. Right? And the P ratio is 7. One company has P ratio of 7, another one 8. 2 of them have P ratios of 8. And then several have 10. One has 12. Many have 13, etc. Right? Up to 91. Right? So what is mode? Basically, you just have to count to see which one is most frequently occurring. Can you count it? You can pause here. You know, if you're reading this, you know, watching this video, you can pause here. You can count, see which one has is the most frequently occurring number, and you probably find it. It's actually number 13. 13. 1, 2, 3, 4, 5, 6, 7. 7 of them. And that's the 7 13ths. So the mode is 13. If you look at other numbers, none of them has 7. Right? So 13 is the mode. It's mostly frequently occurring P ratio among the 68 companies or stocks. You can if you use Excel to do that, pressure earning ratio to find the mode. You see the same data set. If you put in Excel, this will probably what you're gonna get. And you get a mean of 22.72. How is this calculated? You add the price earning ratios of all 16 numbers divided by 68. Right? The median is 19. Remember how you find the median? sort from low to high, find the middle one, or middle two, and average it. And the mode is 13, as I just said. The range is 84. How do you call it a range? That's the maximum minus minimum. We know the minimum is 7, okay? The maximum is 91. So 91 minus 7 will give you 84. That's a range. And sum is just simply you add up all the P ratios among all 68 companies. You get a sum. And count is how many you have. You have, of course, 68 stocks, right? So you can use Excel to get all the descriptive statistics, such as this. So mean for 20.72, mode is 13, that occurs 7 times. Okay? But what does the plot, dot plot show then? Right? Yeah, you show the dot plot, you probably don't see, very clearly. Right? Another thing is about the skewness. You can compare mean and median, or look at the histogram to determine the degree of skewness. We're talking about skewness, right? Skewness, if for data that is skewed left, remember skewed, left skewed, there's a longer tail on the left, right? This one's longer tail on the left, it's skewed left. And where is the mode? Obviously, remember mode is most frequently occurring one. So the highest point in the curve corresponds to the mode, right? And what is the mean? It could be somewhere here, right? Where is the median? The median should be between mean and mode. I'm not going to tell why that's the case, and I want you to think about that. I can use this as an optional assignment for you to think why the median should be between mean and mode. Why can't median be on this side or this side? Okay, it has to be between mean and mode, right? If the data is symmetrical, right, the median, mean, and mode will all be the same. That we can see, right? It's symmetrical, the equal number of higher values and equal number of lower values, and this is a mode, is also the mean, is also the median. If data is skewed right, like this one, the longer tail on the right, the mode is still the most frequent occurring one, the highest point in curve, right? And the mean is here, somewhere here, and median is always between the two, just as in the case of a skewed left, okay? Skewness. And yet another measure for central tendency is called geometric mean, right? The one we just said, the other mean is arithmetic mean, or mean, just mean. Geometric mean, or G, is the multiplicative average. How do you calculate that? You use all the numbers, observations, x1, x2, x3, all the way to xn. You multiply them, and then you find the nth root, and that's your geometric mean. Okay. For example, for the J.D. Power quality data in the book, you find that there are 37 data points. Now, how do you find the geometric mean? You take all 37 data, 87, 93, 98, etc., all the way up to 173. You multiply all of them, okay? And then you find the 37th root of that. Of course, that's a large number. It's not that easy to calculate. It's actually 2.37 to 10th 77th power as the product of this multiplication. You find the 37th root of that. You probably need a calculator or Excel spreadsheet to do that. And you find that the 37th root is 123.38. That is the geometric mean of this number, J.D. Power quality data. And remember, it's different from the arithmetic mean or the simple mean. Right? Why do we use geometric mean? Actually use very quite often in growth rates calculation. The variation on the geometric mean is used to find the average growth rate for a time series data. And how to calculate that growth rate equals the nth root of xn over x1 minus 1. Okay, that's how it's defined as growth rate. Let's take an example here. For example, This is the revenue of JetBlue Airlines, right? The revenues are in millions of dollars, in millions of dollars. In 2002, this company has a revenue of $635 million. Next year, $998 million, pretty good. And next year, 1,265 million, or $1.2 billion, right? And 2005, 1701 million, and 2006, 2363 million. That's pretty good. So how do you find the average growth rate over the 5 years then, right? And that's where you use the growth rate calculation. You use over the 4 years. 4 years after 2002. And basically you use the xn over x1 and minus 1, and that's the row here. Xn is the largest one, the final one, 2363 over 635, that's over here. And you find the fourth root of that, and minus 1. And how is actually when you spread out, the average growth rate is multiplicative of the first one, the first year, that's 2003 over 2002, that's 998 over 635, 998 over 635. And the following year is 1265 over 998, 1265 over 998. And the next year is 1701 over 1265. The final year is 2363 over 1701. If you notice that when you multiply this, 1701 here and here cancel each other. 1265 cancel each other. 998 cancel each other. Basically all you have is 2363 over 635. That's exactly what is here. Okay? So, and we can calculate that. It's 1.389, the fourth root of that, minus 1, you get 0.389, or 38.9% per year. That's the average growth rate of JetBlue Airlines revenue between 2002 and 2004. In the following 4 years, the company achieved the annual average growth rate of 38%, almost 39%. That's pretty impressive. Okay. Another measure of central tendency is called the mid-range. A mid-range. What is mid-range? Mid-range is a point halfway between the lowest and highest value of x. Remember, it's not always the mean, it's not always the median or mode, but this mid-range is halfway between the lowest and highest value of x. And it's easy to use, but it's sensitive to extreme data values, obviously. You have a really large one or really small one, you find the average between the two, the mid, and that's your mid-range. That number could be affected easily. Okay? Again, for the J.D. Power Associates, the quality data of 1937, in textbook, you have the minimum at 91, maximum at 204. You add the 2, divided by 2, you get 147.5. That's your mid-range. Okay? And the mid-range is higher than the mean, which is 134, and the median, which is 132. There's another term called the trimmed mean, right? To calculate the trimmed mean, you need to first remove the highest and lowest k% of the observations. Now, why do we have the trimmed mean? Let me give you an example. Let's see, we want this class. I know you're all my MBA students, and most of you have some supervisory or managerial experience. You're making, some good salaries. For let's just say for most Americans, the average salary, average income per person is about $35,000 to $40,000 a year. Average household income is about $50,000 to $60,000 a year. So I'm expecting maybe, where you're still working, you're still pretty early in your career, you may be making between, say, $40,000 and $100,000 a year. Okay? Now, if you calculate the means of all of us in the class, we get a number. But what if, say, we have Warren Buffett or Bill Gates joining this classroom, right? And of course, his income, their income is probably, I don't know, say tens of millions or hundreds of millions of dollars, right? If you add that person into the room and you calculate the average, suddenly you may find that our average is probably not, between $50,000, $60,000, $100,000 a year, but rather, several $100,000, a year. And that's kind of way is not truly representative of the small population we have, right, or small sample we have. And it's because of some extra large or small numbers. Okay? Now, what do we do? If that mean is not truly representative of the central tendency, we can use trimmed mean. That means, we can trim them off. We can trim the billionaire out of this list, and then without those billionaires, maybe for the rest of us, we can find a more reasonable central tendency number, right? So that's trimmed mean. So how do you calculate trimmed mean? You remove the highest and lowest k% of the observations. K could be any number you want to define. For example, we can take k equal 0.05. That is 5%. We trim off 5% of the observations. For the p ratio number of n of 68, we want to get 5% trim. To determine how many observations to trim, you multiply k times n, or 0.05 times 68, you got 3.4 for 3 observations. And then what do we do then? We remove the three smallest and the 3 largest observations before averaging the remaining values. And then we will have 5% trimmed mean. Okay. Here's a summary of all the measures of central tendency for the P ratios. The mean is set 22.72. In Excel, you can just use equal average P ratio, you get it. Yeah. The median is 19. Remember what median is, right? The mode is 13, right? You can use mode to get that. Your median can get that. The geometric mean is 19.85. You can use this to get it. The mid-range is 49, right? And the 5% trimmed mean is 21.1. Okay. You can see in this case, the trimmed mean, and median, and even geometric mean are not that much off. Okay. The trimmed mean mitigates the effect of very high values, but still exceeds the median in this case. Okay. So, how sensitive are those different measures to the outliers? Right? If we calculate the mean, it's very sensitive to outliers. So if you have an outlier, Bill Gates or Warren Buffett in the room to calculate our average income, then it's very sensitive. So the median is not sensitive to outliers because median it doesn't matter if you have really extremely highly paid guys versus lowly paid guys, right? The median is not that sensitive. Mode is not that sensitive because most people do not have that much of income. And T-mean or trimmed mean is also not sensitive. So keep in mind which ones are sensitive to outliers. Mean. The rest of them, good measures of central tendency and not sensitive to outliers. Moving average. Sometimes we use moving average, to forecast a new level of series over time. It's a descriptive method. By averaging just 2 or 3 periods at a time, we can still see the long-term trends, but at the same time smooth out some of the short-term variabilities in time series. That's the reason for calculating moving average. Because if you just look at the average or to find the value, you can see lots of short-term ups and downs. That's not really reflecting the true trend. By using a moving average, you can smooth it out, so you get a better sense of the trend. Okay, a moving average is obtained by adding consecutive observations for a number of periods and dividing the results by the number of periods included in the average. You can use any number you want, maybe 3 or 4 or 5, and doing that, one by one, you get a moving average. Okay. There's a 2 and 3 period moving average. This is the average U.S. gas prices between 1991 and 2002 with moving average. Okay. And the blue line here, this one blue line here, is the average U.S. gas price, between 91 and 2002. That's dollars per gallon, right? It's as low as somewhere around $1 per gallon, which was in 97, 98. And then the highest is $1.5 into 2000. Because I guess still much lower than today's price of $3, $4, right? I remember when I first came to the United States in 1986, the gas price was about 86 cents per gallon. I don't know if you remember that, or if you are old enough to remember that. I remember paying 7 cents per gallon for my car when I was a student at Purdue University. I was a doctoral student there, and I remember with $20 I can get a full tank of gas for my car and still have extra to get some snacks sodas from the gas station convenience store. And you probably can't get that today, with $3 or $4, $2, $3, $4 gas price. Okay, all right. Let's come back. Blue is the true average U.S. gas prices, right? If you do a 2-period moving average, that is, you take the 2-year and calculate the moving average, and then you take the next 2 years, calculate it, and next 2 years, 2 years ahead each time, and calculate that. You get a 2-period moving average. That's the red line. You see the red line here, right? This red line here. You can see that there is a variation, but the variation is not as much as the blue one, right? It's smoothed out a little bit. If you use the 3-period moving average, you get a green line. Okay, this green line here. Okay, it's also smoothed out a little bit more, than the original blue line. Okay, so 2-period or 3-period moving averages. The next, let's talk about the dispersion of data. What is dispersion or variation? Variation is the spread of data points about the center of the distribution in a sample. Okay? Let's consider the following measures of dispersion, measure of variation or dispersion. One of them, first one is range, the range of data, which is the maximum minus the minimum. In Excel, you use type equal max, the data range, minus minimum data range. You get it. It's very easy to calculate, but it's sensitive to extreme data values, as you can see, right? If it's a really big one or really small one, the range is going to be affected. Okay? The next measure of variation is called the sample variance. We'll use S squared for that. And in Excel, you use equal VAR, variance data, you get it. Right? And this is the definition. How is it calculated? First, you need to calculate the mean of the data range. And then you use each and individual value observation minus the mean, right? Then squared, and then summed. Add together all of them from the first one to the last one, and divided by n minus 1. The sum divided by n minus 1 is your variance. Okay? It's a very important concept. It plays a key role in mathematical statistics. But it's not very intuitively meaning. What does it mean? What the heck does it mean? It's not that obvious, but it's very extremely important in the measure variance. Okay. Next one is called the standard deviation. Now this is probably the most important or most common measure of variation in statistics. It is the, remember variance? Let's go back, look at the variance. This is variance, right? The sum of the sum of the squared differences between xi and the mean divided by n minus 1. The standard deviation is simply the square root of that. square root of variance. That's why we use S for standard deviation, and we use S squared for variance. To calculate that in Excel, we use equal STDV for standard deviation and data range. Okay? It's the most common measure to use, and use the same unit as the raw data. If the raw data is in dollars or pounds, etc., and the standard deviation is also in dollar and pound. It's also not very intuitive, but you need to learn this. You need to, I guess, you have to memorize, truly understand it, know how it's calculated. Standard deviation, very important. Okay. The next one is called sample coefficient of variation, or CV. Okay, this CV is not your curriculum vitae. Okay, it's not your resume. It's a coefficient of variation. It's calculated by S standard deviation divided by your mean and times 100. Okay, and there's no Excel for formula to do that. You can easily do that. And it measures relative variation in percentage, so you can compare data sets. It requires a non-negative data to do that. Okay. And there's another one measure called the mean absolute deviation, MAD, mean absolute deviation. Also, it's not we're talking about the nuclear age, nuclear arms and nuclear wars, and there's a term called mutually assured destruction. I'm not sure you heard about that, mutually assured destruction. Well, it's not that, it's mean absolute deviation, MAD, right? That's calculated by xi, each in every individual values of the data set, minus its mean, and you take the absolute value of that, because the difference could be positive or negative, but you take the absolute value of that, they all become positive, right? And then you sum it, add them all together, divide by n, and that's your mean absolute deviation, okay? And it's every AVEDEV in Excel is easy to understand, and it lacks nice theoretical properties. It's just kind of data. Okay. Then for populations, the one we just talked about, it was sample variance and standard deviation. For population, the population variance, we use the sigma squared, right? And the difference between population variance and sample variance, the equation is we use n, not n minus 1. Okay, it's xi minus mu, the population mean, squared, summed, divided by n, that's your population variance. You take a square root of this, you get a sigma, the population standard deviation. Okay? Remember the difference here. For population, just n. For sample, is n minus 1. Okay? Coefficient of variation is used for comparing variables measured in different units or with different means. And it's a unit-free measure of dispersion and expressed as a percent of the mean. We said CV equals S over X bar times 100. It's only appropriate for non-negative data. It's undefined if the mean is 0 or negative. Okay. Let me give you an example of applying central tendency with dispersion in applications. Like, for example, in this case, in manufacturing, right? You have two machines. Machines like drilling holes on a steel plate, for example. This is a machine A. You have machine B, right? And for machine A, this is the distribution, of your of the holes you drill, okay? And it could be as low as like a 4.98A, or could be 5.012. The holes could be larger than 5, and smaller than 5. This is the variations, right? And this is the distribution. Okay? The blue bars are distribution. This one machine. Yeah. The desired mean is 5 millimeter. Where you drill the hole, that's could be larger and smaller, right? And so for the machine A, the center or the average, it seems to be around 5 of the desired mean, but the variation seems too much, right? And for this machine B, this is the distribution, right? And the variation is smaller. You see, it's 4.9, or 5.040304. It's smaller than this, and but the mean is not 5, right? The mean is actually over here, right? The peak is here. Which machine is better to you? Which one's the newer machine? What do you think? Think about this for a second, 2 seconds, 5 seconds. Which machine is newer? Which machine is older? Okay, come back. Machine A is old machine. It's worn out, even though on average it's fine. You get the average around 5, but you can see a lot of dispersions. Worn out, old machine. Machine B is actually the newer machine. It's more precise. Even though the hole is all smaller, you can easily adjust that. But this machine, machine B, gives you a better precision, and all you have to do is just adjust the size of the hole. Okay, you see that's the one application of the central tendency with dispersion in manufacturing. Okay, there is a theorem in statistics called the Chebyshev theorem. Chebyshev theorem. Okay, what the theorem says is something to do with standard deviation. It says that for any population with a mean of mu and standard deviation of sigma, remember this for population, the percentage of observations that lie within k standard deviations of the mean must be at least 100 times 1 minus 1 over k squared. Okay, so for example, if k is 2 standard deviations, so 1 times 1 minus 1 over 2 squared is 75%. So what it means is that for this population, at least 75% of the observations will lie within mu plus minus 2 sigma, 2 standard deviation. Okay, so 75% of data should be within that range of 2 standard deviation plus and minus. Okay, if k 3 standard deviations, you calculate that, you can check with every theorem. You got 88.9, right? So at least 88.9% will lie within 3 standard deviations. Okay? You can apply this to any set of data, but this limit tends to be too wide to be very useful. Okay? Yeah. Then there's the empirical rule here. The empirical rule says that the normal distribution is symmetric and is also known as a bell-shaped curve. You probably heard about normal distribution or bell-shaped curve. Right? And the empirical rule says that for a data from a normal distribution or the data that follows the normal distribution, a bell curve, we expect that for k equals 1, about 68.26% will lie within 1 standard deviation. 95.44 will lie within 2 standard deviation, and 91.73 will lie within 3 standard deviation. Okay? That's from the empirical rule. The reason for that, we'll get to that later on. But for now, let's just remember that. You'll be okay. Right? So I think it's better to look at this from a chart. The distance from the mean is measured in terms of number of standard deviations. For this population, the mean, the mu, right here, mean the mu, right? And then we can calculate the standard deviation, right? And the mu plus standard deviation, 1 standard deviation here, mu plus 2 is here, mu plus 3 is here, and mu minus 1 is here, minus 2 and minus 3. Okay? If this distribution, if the frequency distribution is a curve like this, a bell curve, a bell-shaped curve, or we call normal distribution, what this empirical rule is telling us is that between minus 1 sigma and plus 1 sigma, okay, that's this range here, between here and here, that is this area under the curve from here up all the way here and come down here, you should have about 68.26% of all the observations. Let's take example. Let's say the height of people. Let's say You take the average height. I don't know average height of Americans. I think it's probably 5'9", 5'10". I think I'm around the average here, right? You say that if let's assume that the height of people's height follow normal distribution, and then the mu is 5'9", 5'10", right? And then we can expect, or let's say the I don't know the standard deviation. Let's say assume the standard deviation is 5 inches, right? Then mu plus 5 inches and minus 5 inches, you should have 68.26% of people in this range, right? If you use 2 standard deviations, there's a wider range from here to here, you expect to find 95% of people, right, within this range. If you use 3 standard deviations, here minus 3 standard deviation, minus 3 sigma, and plus 3 sigma here, you expect to see 99.73%. In other words, 99.73% people will have their heights between plus 3 sigma and minus 3 sigma, right? And of course, there are still people who are taller than this and shorter than this, but not many. It's probably less than 0.3%. So no upper bound is given. Then data values outside are rare, less than 3%. What about those numbers that really go beyond 2 sigma or 3 sigma? We call those unusual observations if they lie beyond the 2 sigma, over the plus 2 sigma or less than minus 2 sigma. We call it unusual observations. If they're beyond the 3 sigma, we call the outliers, real outliers. Okay? And I want to introduce another concept of standardized data. Okay? Why do we standardize data? Because the standard deviation could be large or small, and then your bell curve will stand on normal distribution. Normal distribution could be tall and skinny, or low and fat. What do you do then? And you can standardize the data. If you standardize data, we can have a uniform set of data and probability distribution. Then we can use standardized tables to find the proportions that we need. Okay? A standardized variable z, or z called the standardization or z transformation, redefines each observation in terms of number of standard deviations from the mean. So how do you calculate z-score or z-number? Standardization for a population, you use each individual observation xi minus its mu, which is the mean, right? And divided by the sigma standard deviation. A negative z value means the observation is below the mean, right? And for sample, we use xi minus x bar divided by s standard deviation to find a sample standardized z-score, a z-number, a z-score, standardized score. Okay? And positive z means the observation is above the mean, of course. Right? Next, let's talk about the percentiles. Okay? Another way to describe data. Percentiles are data that have been divided into 100 groups. Right? If, for example, you have your bachelor's degree, you probably also have had your SAT scores, from the test that you took before, a long time ago, some time ago, right? And if we divide the number of SAT scores, for example, into 100 groups, equal number of groups, and then we can calculate the percentiles. For example, if you score in the 83rd percentile, that means on a standardized test, that means that 83 of the people, test takers, scored below you. You had 83rd percentile. Right? That's percentile. Other than percentile, which is used most often, we can also use decimals. Decimals are the data that have been divided into 10 groups. You can have the first decile, that's the first 10%. Second decile, the second 10%, etc. You can also use quintiles. That's the data that have been divided into 5 groups. First quintile is first 20%. Second quintile is for the first 40%, etc. You can also use quartiles. Probably heard more about that. Heard about that very often from the quartiles. You divide the data into 4 groups: the first quartile, second quartile, third quartile, and fourth quartile. Right? Each consists of 25% of the total. Okay? Percentiles. Percentiles used very often are used to establish benchmark for comparison purposes. For example, in healthcare, in manufacturing, in banking industries, they use 5%, 25%, 50, 75, 90 percentiles. Okay? And the quartiles is used in financial industries a lot. Okay? 25, 50, and 75%. That's quartiles, 4 quartiles. Are commonly used to assess financial performance and stock portfolios. Percentiles are used in employee merit evaluation and salary benchmarking. For example, your boss may tell you, hey, you get the pay raise, of 5% next year. Very good. You multiply your previous year's income by 5% and add that, then you get your new salary number. That's percentile. Okay? Another tool for exploratory data analysis is called the box plots. This is kind of like old way of describing and analyzing data, but people don't use it very often, but it's good to know. It's a useful tool for exploratory data analysis, or EDA. It's also called the box and the whisker plot. I'll show you why it's called the box and the whisker plot. Okay? It's based on a 5-number summary. Okay? The 5 numbers are the minimum, the maximum, first quintile, second quartile, and third quartile. Okay? And let's consider 5-number summary for the 68 PE ratios. Okay? The minimum is 7, maximum is 91. The first quartile is 14, second quartile is 19, which is also the median, and third quartile is 26. Okay? If you put it on a box plot, it's displayed like this. It's like a box and the whisker, right? That's why it's called a box and whisker plot. Okay? The box plot shows the central tendency, dispersion, and shape. Where is the central tendency? Right here, the second quartile, or the median, right? And also the dispersion is shown by the first quartile and third quartile, and the minimum and maximum. This is dispersion and dispersion. And the shape, by looking at the number where the second quartile is, you can know this data set is skewed. Skewed left or right, the longer tail is probably seems to be on the right. Okay, so that box plot does show central tendency, dispersion, and shape. Okay. There's another term called mid-hinge. Right? Mid-hinge is the average of the first and third quartiles. Q1 and Q3 altogether divided by 2 is called mid-hinge. On the box plot, you have Q1, you have Q3. Remember, Q2 is somewhere over here, right? But what about mid-hinge? Mid-hinge is actually the average of Q1 and Q3. So it's right in the middle of Q1 and Q3. Since it's in the middle, it's like a hinge. It's just like a hinge on your door. That's why it's called mid-hinge. Okay? And the name mid-hinge derived from the idea that if a box were folded in half, it would resemble a hinge, like that. Correlation coefficient. Right? Correlation. What's correlation? Sometimes we find data values, parameters are correlated. Meaning, for example, the number of educations a person achieved and versus lifelong earnings. We found more education means more lifelong earnings. So that the two numbers, income and education, seem to be connected or correlated. When one goes up, the other goes up. The other one goes down, the other goes down. So they're correlated. But to what degree they are correlated, right? And when you plot this, income versus education, remember we showed the plot where it's forming a line, a straight line, or not forming a straight line. So that degree of linearity, we need a way to measure that. That's correlation coefficient. Right? The sample correlation coefficient is a statistic that describes the degree of linearity between paired observations on two quantitative variables, x and y. And then any variables, could be education and income, or other things. So the correlation coefficient, or R, is calculated by this equation. Looks complicated? It's not. It's actually quite simple. How do we calculate this? Basically, you sum of the product of the two. This xi minus x bar. X bar is your average, sample average. And yi minus y bar is average of y. You have two variables, x and y, right? Xi minus mean, yi minus mean, and multiply it, and then add together from the first one to the last one. That's in the numerator. In denominator, you have two square roots. The first one is xi minus x bar squared. That means squared and summed. And this yi minus y mean y squared and summed. And you take square roots of both of them, multiply that. That's your denominator. You calculate that, that gives you the correlation coefficient, R. And this R actually is a good indicator of the degree of linearity between two variables. So if R could be close to +1, it could be close to -1, and it could take 0 also. So the value of R, by definition, by mathematical definition, is between -1 and +1. It could be 0. Okay? Remember the chart we talked about last time? Okay? In the case of this is, remember this, two variables, x and y. This is a case of a strong positive correlation. We call strong positive correlation. That's when R, the correlation coefficient, is close to +1, +1, or in this case 0.9, plus 0.9. Okay? If in the case of a strong negative like this, the R value is actually close to -1. In this case, -0.9. Okay, -1. When R is somewhere around 0.5, plus 0.5 or minus 0.5, that's when the chart is like weak positive and weak negative. Okay? When R is 0, that means there's no correlation in this case. Okay? So we can have a way to measure the degree of linearity by calculating the correlation coefficient, and it shows in